So, we've learned last lesson about how to find direction of the magnetic field created by the current. We learned about how to find direction of magnetic field created by the straight wire. But what about if the wire is in a circle, which happens most of the time, and especially like with a solid called solenoid, this or coil, or solenoid, when we have a lot of wires, turns made on something. So that called a coil or solenoid. How we can find direction of the magnetic field created by the circular current or solenoid? So let's consider, for example, so there are two ways to do it. First, let's say this is a wire and the current going, let's say, this way. So from your side it will be anti-clockwise. Now those days not everyone understands clockwise and anti-clockwise due to the all electronic watches, but I hope that you should know that this direction called clockwise, this called anti-clockwise. So let's say current is anti-clockwise. So if I grip it here, the wire, current is that way. So I grip in it like this. Current that way. In which direction is magnetic field inside the circle with the current? In which direction is here? No, here. Here. It's at the tangent of the circle. Tangent is going exactly towards you, that way, inside. And if I grip in another place, it still will be same direction. Inside and out. Still here. I will draw how it looks on the board. So we have a current going this way. And so magnetic field will be, if I grip with the right hand rule, let's say grip here, we have on the left hand side what will be the direction of the magnetic field? It will be into the page, into the board, and here will be out. Do this here will be same thing. Out, in. Here, same thing. Here, same thing. So as you can see, everywhere inside the coil, the magnetic field is out of the page. And they all in the same direction, they adds up. So what we always will be concerned about, unless question asks otherwise, is the direction of magnetic field inside. Because there is the most of the magnetic field. The magnetic field which is outside of the coil, it's like spread out. This is where it's strongest. That's what we're interested in, where it's directed inside the coil. Makes sense how we did it? Using right hand grip rule and gripping it here, we have here it's out of the page, above it's into the page. Gripping here, same story.
Why is it moving too much?
Huh? I grip it, and you see I'm moving around the circle all the time inside the coil, fingers going out. Yes?
What is like, I know what tangent means, like how does it like apply to like this?
Tangent,
Yeah.
if we have, this is the circle, this is my fingers, let's say. Yeah? And at this point, because magnetic field, what the direction at this point? It's not a circle direction at the point. It's at the tangent to the circle. At the tangent here, it will be this way.
So that's where the magnetic field is.
But that's what we will have here when I grip it at this point, I'm gripping it, and at this point inside, tangent going that way, circle going around the current, tangent that way. But now I'll show you another way to find direction of the magnetic field of the circle or solenoid, which I believe you can use either this way or the way that I will show you. I think then this way that I will show you is much easier. So we have the same current, but we do it like sort of in reverse. Now my thumb will be given direction of the magnetic field, and my fingers will be given direction of the current. So if we go current going this way, you see current going this way, what is the direction of magnetic field inside? Out of the page. And if it's inside out of the page, everywhere outside it will be in page, because it needs to go around and close it, because it's there close. So this way you just move your fingers as a current going around, and thumb will give you direction of the magnetic field. I think this is much easier doing like this. Yes?
How do you know where the North Pole is?
Excellent question. We're just about to come to this. So if we have magnet, the bar magnet, and this is North Pole, this is South Pole, what the direction of the magnetic field? Away from North. So this is direction of the magnetic field here. Yeah, outside it will go around, of course. But here it's going away from North. So this is the end of the magnet, and magnetic field will go in that way. Now, if we have the circular current that way, and direction of magnetic field is that way, we can always consider the circle with the current. It has very similar shape to the shape of magnetic field of the bar magnet. So if we have that magnetic, so it's like this. It has similar shape. If you place inside the permanent magnet, the shape of magnetic field will be pretty much almost the same of this circular current and this one. Because magnetic field coming this way, where is the North Pole? And we have here, so magnetic field coming that way. Where is the North Pole? Where on this side will be north or south? North. And south will be here. So if you have magnetic field going that way, because magnetic field coming out of the north, and we have magnetic field going that way, that means here, which pole is it? North Pole. And behind is south. Make sense? Or not? So, do you understand the direction of magnetic field? If we have current going this way, the direction of magnetic field in the center is that way, using right-hand grip rule, yeah? Or this way. Now, if I place bar magnet in the way that North Pole is here, which direction of magnetic field will be? If North Pole is here? That way. What we have here, what the direction of magnetic field?
Yeah.
That way. That means you see North Pole here and magnetic field that way. South Pole here, direction of magnetic field that way. So that's why here, to have the magnetic field same way as it with the bar magnet, we need to have North Pole on this side, South Pole on this side. Yes?
What would the poles look like if the magnetic field was going in?
To have, if I will flip this magnet, what will happen with the magnetic field?
Swap ways.
Will go all opposite direction. Will flip as well. Now, before I continue with this and show you experiment which hopefully clarify everything, can we have monopole, magnetic monopole? So, if you take magnet, permanent magnet, cut it in half. We'll get two magnets with the north and south poles. So we have magnet, we have north south. We cut it in half, we get two smaller magnets, north, south, north, south. We keep cutting, and get to one single atom, which is here as a magnet. And it still will have that single atom, will have north pole and south pole. That's why it is impossible to get monopole, because even single electron rotate in certain direction, create magnetic field with the north and south pole. So magnetic field always dipole. It cannot be monopole. There's always south and north. Now let's do the simple experiment. I will put to this coil, I will connect, put current through it. And we will bring magnet first with the north pole and south pole. We will identify which pole will be on this side of the coil, which pole will be on this side of the coil. And we will check with the magnet if it's correct or not. Our suggestion, or not suggestion, but our reasoning. So, I have current going this way. Current going this way through the coil. You see, it's a coil with a current going this way. What is the direction of magnetic field if current going this way, using this way, magnetic field to that direction? So, if I will bring magnet to it, because it's creating magnetic field, right? If I will bring magnet, what could happen? Pull will attract or repel. So we have that way. So what does it mean? Which pole is on this side? North. So if I bring north pole towards it, what happens? North towards north. Repel. So our suggestion is correct. On this side is the north pole. Now I bring south pole. What happened? And it is clearly attracted. So does it make sense how we identify where is north, where is the south?
Yeah.
Now, let's... So, does it make sense how it works, the magnetic field of the solar?
Yes.
Now, when we have attraction or repulsion, that means some force is exerted. But how big is the magnetic force? So now let's have into the force on the current in or charge in the magnetic field. So, if we have current I this way, and we have magnetic field, let's say into the board, magnetic field. Now, for magnetic field, we have letter denoting magnetic field, we have letter B. For electric field, remember, E. For magnetic is B, and it has unit of measurement. Electric field is volts per meter, or newtons per coulomb, but this one, magnetic field, has a special name. It measured in Teslas. Magnetic field measured in Teslas. And 1 Tesla is a very strong magnetic field. For example, the magnetic field of Earth is something like around 30 millitesla. Magnetic field of Earth is about 30 millitesla. So 1 Tesla is quite a strong magnetic field. And the force acting, and the length, it's important, the length of the wire with the current, L. Then the force is B I L times sine theta. Where, so if we have, this is the current, and this is a magnetic field, that is the angle between them. That the angle between them, angle theta. So, in what angle between them in this case? In this case, what the angle between the current and magnetic field?
I have a question.
Sorry, first answer my question. What is and between the current and magnetic field? 90 degrees. One is this way, another one is one this way, another that way, 90 degrees. Yes, what is the question?
Wait, shouldn't it be in and out?
What do you mean?
Like, is it like-
No, it's not magnetic field created by this current. Excellent question, but we have magnetic field created, let's say, by two permanent magnets between them, or some other source. And we take wire with the current and bring into this external magnetic field. It's not magnetic field created by this current, it's external, by another source. So this is the magnitude, BIL sine theta. And direction of the force we will define using another right-hand rule, but not grip, but right-hand slap rule. Right-hand slap rule. How it works? Your four fingers give you direction of magnetic field, so that way. Thumb gives you direction of the current, and force coming out of the palm. So force will be on this wire, will be up. So wire force coming from here, because you can't, like slap rule, you can slap with this. With this side you cannot like really slap much. So it's coming out of the palm, slap rule, with the force. So you place four fingers, magnetic field, thumb, current, force coming out of the palm. Now, for kids doing SPECH, the actual proper formula is F equal I, if you take it as a vector, cross product B. That is a force acting on the current in the magnetic field is a cross product of the current and magnetic field, but that's not part of the school physics curriculum. So, and the direction will be, if you identify the direction using this, you already done cross product, yeah? So if you find what will be the direction, it will be exactly with this rule. It will be exactly with this rule. But don't worry about the cross product, who not learning it, at least this year, yes?
So for that force formula, is the magnetic field always external?
This we're talking about the external field created by someone, not by this current. Not by the current, something else created, and you bring that current into the magnetic field. Yes?
What's B?
Magnetic field. Or strength of magnetic field, or just magnetic field, which measured in Teslas. So, if you will have magnetic field, let's say this way, and why will the current position like this? What will be force acting? Zero. What the end magnetic field and current? What the end between magnetic field and the current? Zero. Sine zero, zero. So if we replace wire along magnetic field, there will be no force on the wire. Only if it's at the end. And the biggest force will be for what angle? 90 degrees, because sine 90 equals 1. The maximum will be 90. Most of the cases we will be considering when it's 90 degrees between current and force. But between current and magnetic field. So that is the force acting on the wire in the magnetic field. Let's consider now a situation we have two wires with a current. How they will interact. And we will then experimentally check our reasoning. So we have two wires with a current. Wire A and wire B, and they have current in the same direction. So let's find what will be the direction of magnetic field created by wire A at the position of wire B. So we grip using straight line, so we're using this grip rule. And what the direction of the magnetic field here?
To the left, out, in.
Here, in. the magnetic field will be in. Hmm?
Why is it on?
We grip this one, and on this side of wire, how it's going around the wire, and on this side, so it will be coming out here,
Yeah.
and here on this side it will come in. So everywhere here it's in, everywhere here it's out. And here it will be everywhere in. Because that's how it's going around. It's going around like this. Magnetic field created by this wire. So important that magnetic field is into the page. Now let's find what is the force acting on the wire B. What the direction of the force? Magnetic field into the page, current up. What the direction of the force? This way. To the left. To slap. So force on this wire is to the left. Yes.
Why do you say that in between the two wires that's going in is on?
You grip this. I'm talking magnetic field created by wire A. I'm not looking at the magnetic field created by wire B. Only by this one to find what will be the force exerted by the magnetic field created by wire A on the wire B. Now let's do the same thing with the wire B. What the direction of magnetic field?
Onto the wire B, you put the thing as going out of the page.
What are going out?
I mean, going into the page.
Are you talking what will be if you do this? Yes.
I'm saying for wire B.
If we grip B, wire B, what will be the direction of magnetic field created by wire B at the position of wire A? Out of the page.
Good guesses, sir.
And now what will be the direction of the force acting on wire A? Magnetic field out of the page, current up, force this way. So what happens if you place two wires with the current in the same direction? What will happen with them? They attract. They will be attracting two wires with the current in the same direction will be attracting. They attract. You place two wires and they attract the current in the same direction. If we will have, you can do the similar reasoning. If we have two wires with the current in the opposite direction, guess what? They will repel. By the way, I think it was last year was question on the exam about that. What will happen if the current and what will happen with the wires will be pushed up or down. And it was a couple years ago another one. Makes sense this? Let's do experiment. Now we have one coil and I will connect another coil. So, now I connected them in the way that the current in the both in the same direction. Doesn't matter that they encircle, main thing that current here going like this and here like this. So they both have current in the same direction. So let's see what will happen if the current in the same direction. So I place them on some distance, I'll turn in current on. Did something wrong. So, yes. This one, I current going that way, yes. So, yeah, turn this. So now we have currents going in the same direction, both. They clearly attracted current in the same direction, attracted. Now I will flip direction of the current in one of them. I turn it around. So now we have currents will flow in the opposite direction. I put them together and see what happens. They clearly repel each other. So our suggestion was correct. And the last bit of the theory for today, how the magnetic field will act on the charge moving in the magnetic field. Because moving charge, what is electric current? What is electric current? Moving charges, the net motion, overall net motion of the charges. So if we have one electron moving this way, in which direction will be current? To the left, because we say direction of the current where the positive charge, from plus to minus. Electrons will be flying to plus or to minus?
Plus.
To plus. So current is, if electron moving this way, current that way. Make sense? Now let's place its electron, let's say, in the magnetic field. And we will make magnetic field up. So we have magnetic field up. What will be the, probably not up, we'll make it, we have this way, we have magnetic field into the page. Magnetic field everywhere into the page where electrons fly. So, direction of the current to the left, that way. Magnetic field into the page. What the direction of the force?
Down.
Down the page. And what will be the angle between the force exerted by magnetic field on the electron and its velocity? What kind of motion we will get if force will be acting at 90 degrees at the velocity? Circular motion. Circular motion, that is, will be circular. So in magnetic field, charges moving in a circle. In magnetic field, charge will move in a circle. Let's find how big will be. We know that force equal B/I/L sine theta. Now, L, length of the wire, will be distance that electron will cover. So speed of electron times time. Substitute it here, we get force equal B/I/V/T sine theta. And what we get when we multiply current and charge? What the definition of the electric current as a quantity? Do you remember? Charge over time. How much charge came through the conductor in 1 second. From here, IT equal Q, so we get the formula for the charge. Q, IT is charge, Q, V, B, sine theta, where theta is angle between velocity and magnetic field. So that is the force acting on the charge moving with the velocity V in the magnetic field. Let's consider the most simple case.
Theta is like where the right angle is, that's what theta is?
In this case, yes.
Okay.
It
So
can be not
have to be
necessary.
90 degrees.
It does not have to be, but we will consider in the most of the scenarios 90 degrees. So if sine equal 1, we will have that force equal just QVB. Will the electron changing its speed? Will the speed of electron changing? No. There is no force acting along the velocity. So we will have in this case force equal constant. And we will have that force
Force always is constant.
perpendicular.
Is force always constant?
No,
Fine.
not necessarily. In this, if you take looking into magnetic field, electron moving in the just magnetic field, it will be because speed constant. But we might apply also electric field and make velocity change, and so not always, but in this case, yes. when we have force constant and force is perpendicular to velocity all the time, we get circular motion. So, circular motion. That is the two conditions for circular motion with a constant speed. Speed constant and at the right angle to the velocity all the time. Let's find the radius of this circle. Let's find the radius of the circle with the charge we do in the magnetic field. So we have what will act as a centripetal force. What will act as a centripetal force? This one. So we have QVB equals what the formula for centripetal force?
mv squared on
mv squared on r. Rearranging it, we get r equal mv over qv. That will be the radius of the charge in the magnetic field. How it's applied in the particle accelerators and other applications we'll do next time. Any questions? Thank you. Like, subscribe, and donate. Support Ukraine and Israel against Russia, Iran, and Hamas.